So today we're going to talk about gases and start our unit on gases and phases of matter, solids, liquids, and gases, as well as solutions. But today's focus is just on gases. Some of these things are fairly intuitive, some things that you probably already knew or could figure out, but we need to talk a little bit about some of the stuff that's maybe a little bit less intuitive. First of all, you can pause at any point. I also left the PDF of the notes without the problems worked out if you'd rather just copy from that rather than the video. But obviously pause at any point. You do need all these notes as well as watching the video and answering the questions. Okay, so here we go. There are 4 things that can be changed or measured for any gas sample, whether it's in a balloon or let's say a scuba diving tank, or if we're just talking about the gas in a room. And the first one is pretty simple, and you're pretty familiar with it, and that's volume. The symbol for volume is V. The units are going to be liters usually. Sometimes we'll go milliliters. And it doesn't really matter too much which of those we use, at least for the time being, because they're both just absolute measurements rather than being relative measurements. They both just measure how much space a gas takes up. Gases are unique because they do fill their entire container. So the volume of the gas in my classroom would be the volume of the classroom because they bounce off all the walls of their container. I've got a little PhET thing to show you here. So basically, if you just look at the gas particles inside of this tank, and I can pump some more in there. Okay, they bounce off all of the walls of their container. They fill their container. So when we talk about a gas sample's volume, it would be the entire volume of the container. Okay, pretty straightforward. The next one is temperature. Temperature is symbolized by T, measured in kelvins, which are symbolized by K. Kelvins are used instead of degrees Celsius because the degree Celsius scale, like the Fahrenheit scale, is not absolute. In other words, you can have negative Celsius temperatures just like you can have negative Fahrenheit temperatures. The Celsius scale is completely based upon the freezing point and boiling point of water. So that's why water freezes at 0 degrees Celsius, because that's what they base the Celsius scale on, the freezing point of water. Water boils at 100 degrees Celsius. Because again, they base the Celsius scale on the freezing and boiling points of water. And that's perfectly fine, except when we talk about gas samples, and we talk about their temperature, we're talking about their average kinetic energy. In other words, again, if I look at my sample, the temperature here, which you can see the reading here is 295 kelvins, that is describing the average kinetic energy of the particles in the container. Now, I want to first talk about the word average, because not all the particles are moving at the same speed, and therefore not all of them have the same kinetic energy, even if they are the same size. So kinetic energy depends on the mass of the particles and their velocity. And so let's assume that these are all, let's say, helium atoms moving around inside this box. So they would all have the same mass, but their kinetic energy would be different. Because they're traveling at different speeds, different velocities. But when we talk about the temperature being 295 kelvins, we're saying the average kinetic energy of the particles is 295 kelvins. The other part is the whole relative versus absolute part. Because kelvins don't go below 0, because they're describing kinetic energy, you can't go below 0 kinetic energy because you can't go below 0 velocity. And so even if these particles were completely still, they would still have some Kelvin temperature. If I lower the temperature here, you can see the particles slow down and slow down and slow down, and the Kelvin temperature is dropping, but the slowest they can go would be 0 kelvins, because that would mean 0 movement. And so that's the important thing about kelvins. All right, and I'm not going to take the time to go all the way down to 0, but you get the idea. Okay, and if we're given a Celsius temperature, like let's say the room is, let's say the room is 25 degrees Celsius. Kelvins are just going to be degrees Celsius. So let's say we're talking about room temperature is usually about 25, plus 273 would give us 298 kelvins. We always want to do that conversion whenever we're given a Celsius temperature. Okay, the third property or variable that we're going to look at with gases is number of particles, moles. We're not going to do that right away. We're going to kind of set that aside today, but all you need to know for right now is it's symbolized by the lowercase n, and it's pretty self-explanatory. It's just when we talk about a sample, how many particles do we have in that sample? So let me heat this back up a little bit, and if I add some more particles using the little bicycle pump over here, obviously my value for n would be going up because I have more particles, therefore more moles of particles. That's n. That's it. Pretty simple. Okay, the next one that we have to spend a little bit of time on is pressure. Pressure is defined as force divided by area. So if you accidentally step on your friend's foot and you're wearing a flat-soled shoe, and that pressure, which is going to cause the pain that they feel, is going to be dependent on your mass and therefore the force that you're able to exert due to gravity, divided by the area. So the more area there is on the sole of your shoe, where it's coming into contact with their foot, the less pressure there is because your denominator is increasing. The same size person wearing a high-heeled shoe stepping on your foot is obviously going to decrease the area, which would increase the pressure. So gases aren't, the same as shoes. We're not talking about one instance of, a force colliding with, over a certain area. With gases, we're talking about billions and billions and billions of individual collisions of gas particles with the walls of their container, and that's what gives you this pressure reading that you see right here. In this case, it's about 0.5 to 0.6 atmospheres. Depending on how many collisions these particles are having with their container and how forceful those collisions are. So we'll come back to that a little bit later. But pressure can be measured in 4 different units, and actually more than 4 different units, but these are the 4 that you're going to see a lot. Atmospheres, which are ATM, pounds per square inch, PSI, millimeters of mercury, mmHg, and kilopascals. Are the most common ones used. In chemistry, we don't actually use PSI a whole lot, but I wanted to introduce that to you because that's what we use in everyday life a little bit more. For example, if you're driving and you want to make sure that your tire pressure is what it's supposed to be, you'll read the number on the side of your car door, on the inside of your car door. It'll tell you how many PSI to inflate your car to. It's usually somewhere between 30 and 35 PSI. So pounds per square inch of pressure being exerted on the inner walls of your tire. And then the other 3 are used a little bit more commonly in chemistry, so we're going to focus a little bit more on those. But down below there you can see normal standard atmospheric pressure at sea level is 1 atmosphere. So that means that the atmosphere, just like the Celsius scale, 0 is the melting point, freezing point of water. Well, they base the atmosphere scale for measuring pressure on Earth's atmosphere. Very logical. On a normal day at sea level, we have 1 atmosphere of pressure being felt by everything and everyone. As you travel above sea level, St. Louis is only about 500 or 600 feet above sea level, but there's a little bit less air, and so a little bit less air pressure. If you go to Denver, that's a bigger difference. You go up to 10,000 feet in the mountains, that's a much bigger difference. You're going to actually see like 0.9 maybe or a little bit more than that atmospheres. So maybe, depending on how high you go, 85 to 90% of standard atmospheric pressure. And there you can see the other values that mean the same thing. So 1 atmosphere would be equal to 14.7 psi or 760 mmHg or 101.3 kPa. So a quick conversion here, you can try this one. Just use dimensional analysis for this one. And I'll give you a second to give it a shot. Starting with 240 kPa, convert that into atmospheres. Okay, so you should have gotten about 2.4 atmospheres, just dividing by the relationship between atmospheres and kPa. There's 101.3 kPa equal to 1 atmosphere. So putting it in atmospheres makes it pretty easy to think about, because atmospheres are equal to the pressure you're probably feeling right now, normal atmospheric pressure. And so what's the pressure inside of a tire? If you're able to shrink down and somehow get inside of a car tire, you'd be about 2.5 times more pressure. So it'd be very, very high pressure. Probably wouldn't feel too good. How do we measure atmospheric pressure? It's measured using a device called a barometer. And the way that a barometer works is you've actually got mercury inside of this dish, and it's also inside of this inverted glass tube. So you basically fill up a glass tube with mercury. You have another dish of mercury, and you, if you can imagine, you wouldn't do this with your finger, but if you can imagine putting your finger over the open end of the glass tube, flipping it upside down into the dish of mercury. If you've ever done this when you're washing dishes with water, fill up a glass of water and then pull it up from the bottom. As long as you keep the top of the glass underwater, the atmospheric pressure will support the water inside of the glass in the sink. Well, mercury is heavier than water, so it doesn't quite support all of the mercury to keep the tube filled up, which is why you have this empty space here at the top. And then as atmospheric pressure, let's say, rises, it's going to push down harder on the mercury in the dish and push more mercury up into the column. So if you go back to our units for pressure, normal atmospheric pressure in millimeters of mercury is 760. And so what that means is if you were to take a meter stick and set it alongside this barometer, this would be, barometers are very tall, but if you set a meter stick alongside this barometer, the height of the mercury on a normal day at sea level should be 760 millimeters of height. So that's how a barometer works, and that's how we basically know that the pressure is changing outside, and therefore a cold front or a warm front might be coming depending on changes in barometric pressure. Usually if the barometric pressure is dropping, that means there's less air pushing down out here on this dish, and that usually means that low pressure, or it does mean that low pressure is on its way, which usually means cooler air, sometimes rain or snow or whatever. Okay, so the next section here is on relationships between pressure, volume, and temperature. I'm going to actually ask that you just go ahead and copy the notes from the PDF that's on Classroom, and then I'll go over these in class next time. We've gone a little bit longer than I anticipated. We're already 13.5 minutes, so we'll stop the video lecture here, and but do copy the rest of the notes from the PDF, and I'll take questions over those pressure, volume, and temperature relationships in class on Wednesday.